Well, thank you so much for coming this morning. It's a early morning session here, but yeah, if you're applying model predictive control and you're also trying to find that measurement that you need in model predictive, but you can't afford to wire it in, and you're looking at using wireless, then this is the session to be in. So we'll be talking about how you can effectively apply wireless with model predictive control. So that's really the topic today. I'm just sort of introducing and doing a little bit of the summary, but the main speakers are Bailey Roach from University of Texas, so I'll let her introduce herself. But we've been working very closely with University of Texas, and then Willie will be talking then about model predictive, how the change you need to make to use wireless control. The agenda is shown here. We are working on a new process with the University of Texas in terms of control and instrumentation, and so it's heavily instrumented with about everything that Emerson makes right now. So it's really a very, very interesting process, and so I think you'll enjoy that discussion. So with that, I'll turn it over to Bailey Roach, and she'll tell you about what they're doing there.
Hi, I'm Bailey Roach. I am a PhD student at the University of Texas. I work on the divided wall distillation column. This is my baby right here. We have a collaborative effort with Emerson. Luckily, they're just down the road in Round Rock, and they supplement us with our control operations and help with the research that we go on. So a little bit of background of our Pickle Research Center. It's a collaborative effort, started in 1984. There was a need between university research and the industrial needs, and so we have our pilot plant out here. Currently we have an 18-inch distillation column, and our divided wall distillation column, which just went up this summer, we pressure tested it last week. So hopefully we'll be up and running for you very shortly. I've been doing a plug for, we'll have results from our model predictive next year. So be on the lookout for that. But unfortunately, due to research, we were not able to have results this time. And I also want to do a special acknowledgement. Eastman Chemical is one of our big funders for the divided wall column. So they've given us permission to share a lot of these results. So here's just a little bit about the divided wall column. First, let me give you a little background why a divided wall column. Traditional distillation can separate binary, so you'll have a feed come in, and then out the top you'll get one component, and out the bottom a different component. But with the divided wall distillation, you can effectively combine two columns into one, and so you can actually get a tertiary separation by having the wall in the middle. However, by adding the wall, you also add additional degrees of freedom. And so this technology isn't new. It was funded in the 1940s. However, it's just not in use a lot in industry right now because a lot of the control hasn't been studied. And so there's a lot of unknowns about how to actually control this column. And without being able to control the column, you don't get the energy savings from it. And so a divided wall column, if effectively controlled, you can have anywhere from a 30 to 50% energy savings over traditional distillation. As well as you save space in your plant, it's really a need to know how to control a divided wall column. So Link and Lubin published a paper on studying a benzene, toluene, and xylene separation. And they based the composition control of the overhead, the side stream, and the bottoms flow on the temperature measurements in the column. And so this kind of inspired us on how we will study the control of our distillation column. And so they used the temperature measurements for an inferred composition. And so for our column, it's about 28 stages. And luckily, we were able to have temperature transmitters on 19 of those stages. So we will not use all of them, but we have the flexibility to be able to change very quickly and effectively which stage we'll be controlling off of. So it'll be a huge control study. And we've done preliminary looking at which stages we'll want to control off of, but we won't really know the results of these until we're actually able to run the column. We'll be using model predictive control on our column. So like I said, by having the wall, you add additional degrees of freedom. So one of the most important stages in the divided wall column is actually the split. So here you'll want to call the column the pre-frac side. So this is where the feed comes in. And then this is the main frac side. So the side stream product shown here is coming out here. So you have your A product, B product, and C product. The idea behind this wall is to separate the feed and be able to take out the side stream. And so you actually don't want to do the split 50-50 at the top of the wall. We don't know what the ideal split is, but done in modeling, it's about a 25-75% split. But this split is very important for us. And so that's one of the manipulated variables we'll be looking at. So normally you manipulate the reflux at the top of the column, the reboiler steam flows, and then our liquid split, and then the side stream, how much we'll be pulling out here. So it's imperative to have an effective control just because each of the variables interact with each other. And for my project, we'll be looking at the steady state, but further down the line, we'll actually be looking at disturbance variables. So we'll change the feed flow and the feed composition. Here's a rough flow diagram of what our divided wall column looks like at the pilot plant. It's a 6-inch column, about 30 feet tall. When you have in industry a column that's much larger, you're actually able to internally do that split at the top of the column. But unfortunately, with a 6-inch column, we're just not able to control that liquid level. So what we're doing is we have a total trap tray in the column. So we'll be pulling all the liquid out and putting it into a vessel and pumping that through a heat exchanger just so we'll return the liquid back to the column at the same temperature. And then we'll be controlling the split with 2 control valves, as well as there will be a control valve for the steam. And then for the side stream split, it's the same idea. There's a total trap tray in the column. We'll pull that out to a vessel, pump through a heat exchanger, and then split. It's a continuous process, so our products will just go back to the feed tank. So the red circles indicate that it's actually a wireless control valve that'll be operating. We'll have the ability to transfer between wired and wireless. And so we're using wireless in very critical loops. So we're not afraid of the wireless technology. So why wireless for UT? Before I left for this conference, our plant manager wanted me to stress at each presentation how much we love wireless at our research facility. So if you run into him, let him know that I told everyone. We've had a huge history of wireless. Our divided wall distillation will be outfitted with several items, but our pilot plant is over 30 years old. It's, as you can see in the previous picture, I mean, we have a lot of equipment out there. And with research, you're constantly changing out. And so by having wireless, it just makes it so much easier for us to install items. It's cheaper for us as well. We're not constantly running a conduit. And the flexibility of being able to change. Like I said, we have 19 temperature transmitters on our column. In total, throughout the process, we have 30. And so our operator would still be running conduit if we had to have all of them wired. So we're very, very big fans of wireless at UT. I hope I set you up well, Willie, to go into the MPC.
Good morning, everyone. I was so listening that presentation that not jump immediately, was thinking. Very nice introduction. So let me continue. And at this point, I may notice one or remind one figure Bailey told about those huge savings which DWC column may provide. 30 to 50% is something incredible. And this is just concept or invention of that column, which is from 40s already. So there are some reasons why this was not implemented. And one of those, what we may see that really might be possibly too rigid solution for instrumentation and control. So definitely part of the strategy is really provide this flexibility from the beginning, and really essential part of the strategy should be model predictive control, because it's really hard to imagine effective column control with no MPC at this time. And I took part in the project after all control strategy was developed, and Terry worked on that, and Bailey worked together, and there is all local control loop developed, and we start discussing about how to implement MPC. Essentially, there was some, we have Predict Pro, and there's this MPC, not quite suitable for wireless control. But when we start discussion, we came up to certain conclusion that, well, there's very close. And how it solved, I just tell you story, what is the concept of wireless MPC. Definitely, general requirements is like any control, wireless control. It means provide stable operation at significantly slower scan rate than with wired control. Scan rate can change as a transmission period changing. Achieving significant performance change, definitely we cannot expect that our performance will be better, but we need to develop strategy that will not, performance will not degrade. And what is important for any control that provide switch over to safe mode of operation. Definitely we need to make it quite smoothly. So let's look how MPC works. And this is very simplified diagram. And what we see here is really process. There is this measurement coming here. In that diagram, it's wired measurement, and it's compared with modeled output, which is here. If there is a discrepancy, we may correct this model prediction here. And modeled vector output is compared with set point trajectory, comes to control algorithm, and we developed manipulated variable for the process. Just a simple explanation. What is important for us to consider how we'll behave here. You see, this will be wireless measurement at this point. So behavior should be somewhat different. And let's see what definitely logic tells us. Since at wireless measurement we got transmission and we get value of parameter, and then several MPC scans, this value stays. So we cannot correct our prediction based on that model. You see, we cannot compare and correct prediction. So exactly one rule we need to apply in the wireless MPC. Do not apply prediction correction until a new wireless measurement value is available. So same with input parameters, which in our case are disturbances. And since we don't apply prediction correction, it means that in meantime, all other MPC scans until a new measurement coming, we need to work based on simulated value. It's really MPC immediately create that advantage with which PID has not in obvious way, because it has model. So MPC really, when we don't have measurement, we can work on simulated value. And after this short consideration, we said, well, MPC is really control tool or technique which very easy can be implemented with wireless control. Let's see on diagram how it happens in details. So MPC prediction is corrected. Every MPC scan is in 3 basic steps. So first step is really updating time. So we shifting that diagram to the left. Just we updating what was K becomes K plus 1 and so on and so on. So just step 1 is shifting prediction. Step 2, we need implement on the output effect of those input changes, what happened on the MPC input. And final step, we need to correct those simulated prediction with actual measurement, because whatever model is, This is that gap which is here. Whatever model it is never perfect. We need to believe measurement. So what is step 3 is correct process prediction or model prediction. So what it means correcting? Correcting it in that diagram here is shifting up our predicted trajectory. So coming again to our first diagram, we say we cannot make every MPC scan this shifting of our prediction. It's a little bit kind of deficiency in MPC operation, but not significant. Now let's see whether such or similar mechanism exists already for other cases than wireless control. And one of those cases is when analog input status, measurement status is bad. What MPC should do that? And in many MPC designs, in particular in our Predict Pro, we have such a feature that we can say that when analog input or measurement status is bad, MPC still should operate certain number of scans. And that means the status when status is bad, so then we use simulated value and MPC performs operation. Very similar like in wireless control, what we intend to do. So someone who applies MPC knows this very well, that we need, when we configure MPC, to set this feature. Next, very similar MPC behavior we observe with lab measurement. Lab sampling is really some value which is taken at much slower pace than MPC operation. Within one lab sample, we may have 10 or even more than 10 of MPC controller scans. And definitely we can not use those lab value for MPC model update. So what we are doing here, they're shown here, that we take a new lab value, we update at this point MPC model, and then we use simulated value of that measurement, of that process output, and MPC operates in such way. So lab measurement is kind of very good analog to wireless measurement, and as well it has feature that not every time is regular. It's really, we got measurement with much slower pace than MPC operation, and it's as I said, it's really very similar to wireless. Well, so now we are coming to conclusion that to develop wireless operation, we need to develop wireless measurement which will conform to those rules. So first of all, if measurement is transmitted, status should be good. Otherwise, it should be constant. And that constant status, it could be bad, but it's really not sounds good in principle. But what we just assume more proper is should be constant in wireless control. So if it is status constant, so MPC will be working based on simulated value. And that is principle of wireless MPC operation, provided analog input really deliver that measurement status. And that is exactly what we need to do. That at PID, this is shown PID loop level, we develop special, let's say, extension of original measurement, wireless measurement to which will be used in MPC, which generates status in the way what I discussed a minute ago, that really status will be constant when there is no new measurement, and status will be good when there is new measurement transmitted. We need to set some additional parameters or settings which fortunately are present in Predict Pro. That's exactly what we noticed after discussion. So-called SIM time factor. SIM time factor, which tells how much MPC will use measurement, how long time MPC replace measurement by simulated value if measurement status is failed or constant. And that SIM time factor is measured in time to steady state, so it's very, very significant time, even for wireless control, because time to steady state usually it's 3 time process constant plus dead time. Essentially, it's wireless measurement should be delivered in much shorter period of time. In a normal MPC operation over time to steady state, we have 120 scans. So at that point, we assume that wireless control might be, we tested with that wireless measurement period has 16 MPC scans. That's still significant, and I think we might extend quite a bit. So there is settings in Predict Pro already. I need to say that one more settings I didn't notice here. We need as well set up when this period time is extended, what mode MPC will be shedding to. And usually it's at local mode or manual MPC. So that's as well as one of those requirements we said at the beginning, that if wireless fail, we need to have safe exit from that strategy. Well, that is summary what we discussed exactly. I will not repeat because I kind of already. So there is, in a short, new value, status good, where is no new value transmitted, we just status is constant, and the MPC uses simulated value. There is summary of that concept. Very simple and clear, and fortunately all kind of features in Predict Pro were already there, so it was easy to assemble. This is MPC operation screen. When we set MPC for that wireless operation, there is one interesting graphics here, which is timer. It tells really what time left to go to local mode. So you see, this is in our, we had 2 minute, 2 minute was time to steady state in our case. It's 120 second scan. A normal MPC scan is 1 second. So in that case shows 1 minute 59 second left to go to local mode. And that's kind of nice feature. In general, we need really to set up that maximum SIM time factor in such way really to account for maximum transmission period. If we have several wireless measurements which work with MPC, safe way would be to add them together and set up this SIM time factor as a sum of transmission periods. Okay, now we go to MPC Classic. So MPC configuration for wireless is exactly same as for normal MPC. So I will not go into detail, just let me mention those few general rules that we select MPC function block and make configuration of controlled, manipulated, constrained, and disturbances one by one, setting those basic parameters for every variable here, and primary, what is really important, setting connection of function block to the source of the signals. For the simulation, we used a simple model as possible, just based on Bailey recommendation here. Essentially, the main problem or main issue was test wireless operation at this point. And procedure for model development is a typical one here. I have to mention one thing, and which is still a problem we may disclose in more details. The model was developed for using wired connection in simulation. So there are many issues to discuss how we develop model from wireless instrumentation. There is some separate issue. But at this point we may say that we use same model for wired control in case we switch to wired and wireless control. Model doesn't differ. We perform standard testing. This is automatic testing. We go to model review. From model review, we model validation or verification. Then we go to controller generation, which everything performed automatically in Predict Pro. But on those automatic procedures, it's very important to keep eye on those all steps, and it's worthwhile to know what results are. Finally, this is control strategy, which is set on optimizer screen. Essentially, strategy is very simple, just for temperature. I use kind of generic name. Bailey is not happy of that, but we name those in MPC such way, and upper, prefrag, lower and bottom temperature, we need to keep on the target here. And that's as simple strategy as we can imagine. Since we worked at this point on simulation can be set for operation in wired mode and wireless mode. So to set in wireless mode, we may as well select maximum transmission time, which is in that point 8. In our testing, we used 8 and 16 MPC scans. So what we observed when we switched wireless control, and what this is shown on the screen. You see, this is step response, which in general, I would say, does not differ too much from wired control, but we notice some bumps here, small bumps. And that's easy to explain when we know the principle of operation, that at this point, you see from the beginning up to before bump, MPC works on model. At the point of bumps, new measurement is coming and model is updating. This simulated process output is updated. So this is why bumps are coming, and that's something we need to live with. There is no other way to kind of avoid this. And this is, we may say, effectively a little bit performance might be smaller, but as we come up to measurement, we measured automatically in simulation absolute integrated error. So happen to be the performance, I'll tell later, doesn't change so much. Now, on that slide, it shows a real value, measurement value, which comes from wireless. See, this is measurement is steady, this is steady, this is steady. And this is, we work on the simulation up to that point. At that point, coming new measurement, so why we notice in that simulated trajectory, small bump. Again, from here to there, we worked on simulation. It's hard to imagine that MPC can work on that constant value. So that's really, everything works like in theory here. Well, and now we are coming to the conclusions. We observed stable operation using wireless control for significant time period of wireless. As I said, we tested 8, 16, and stable operation definitely might be provided even for longer transmission period. Process model for wireless MPC is even more important than for wired MPC. This is something what at the start we need to realize, that we are happy with that performance of operation, and we know that model quality for MPC in general is important. For wireless is even more important, because MPC works significant number of scans, let's say, if we say 16, so it's like 90% or 95% of operation is based on purely on model. So model quality should be really high. MPC is really quite well prepared for wireless operation. We just need put mechanism to handling status of wireless measurement, which corresponds to MPC proper functioning. That's all what we need to do. And by the way, it's just better prepared than PID because model is there. And wireless MPC is in general, we adding some new feature of the product, no doubt. Okay, Terry, can you summarize?
I hope you found this to be of help. If you want more information on wireless, and one thing I wanted to mention was that if you haven't seen this book before, this is a new book that we just came out with on wireless control. There's a whole chapter on model predictive using wireless. So if you want more detail, then this has got that chapter. So much for